Okay. Welcome to the last lecture of this module, where we aim to prove the so called and very famous isoperimetric inequality for planar curves. But for before we start that, we need to gather some information on simple closed curves in R2. As the name suggests, suppose A is a positive number. A simple closed curve in R2 with period A is a regular. We know what is regular, smooth, that is we have tangent at every point, function gamma defined on entire R to R2. So, instead of defining it on an interval, I define it on the, I can extend it to the R to R2 such that gamma t equal to gamma t prime if and only if t prime equal to t plus some k a, k is some positive integer. So, what it mean here? If I have a curve defined on some interval, say alpha beta, now and I also have that. So, I have a curve alpha beta which is like this, that it intersects itself with at the same point at one point only, and then everything is smooth. Then actually I can extend it to the entire R with the period beta minus alpha. That is what I mean, right. For instance, you can check the sine curve. Now, you consider the sine curve with this portion. So, from 0 to 2 pi, I have this curve. Now, I can extend it periodically to entire R using the formula that sine alpha plus 2 pi is sine alpha, but this is not a closed curve, this is not closed, whereas we are concentrating on closed curve. For instance, if you say, so example, if you look at this curve, gamma theta equal to say sub r cos theta sin theta, theta in R, what will you give it, give us? Okay, for theta in 0 to 2 pi, this will give us circle. But now I go for any theta, theta plus 2 pi, since cos and sin are 2 pi periodic. So, if I extend it, I remain on this circle, I do not move anywhere other than that. So, this is a simple closed curve on R2. Now, there is a great theorem which we cannot prove with our tools, it needs some kind of a more advanced techniques and complex analysis. And okay, before that, well, here itself. For a simple closed curve, we define length of the curve to be L gamma 0 to a gamma dot t norm dt, and you can easily see that if gamma is unit speed, length gamma is equal to a, where a is the period of the curve. Okay. So, this is just a definition, and this definition makes meets every kind of a demand we may make. Now, there is a very famous theorem, as I was telling, is called Jordan curve theorem, and which we cannot prove with our existing tools we have so far developed, but we will use the statement. If you look at the statement looks like very trivial, but to prove it mathematically, it needs lot of effort. So, let us be satisfied with the statement only. So, statement is gamma be a simple closed curve in R 2. Then this entire plane R 2 can be divided into disjoint union of 3 sets, not region, 3 sets: interior gamma, union exterior gamma, union points of gamma. What is interior gamma? The shaded portion this part is called interior gamma, that is the area enclosed by gamma. The portion outside, this is called exterior of gamma, that is the area which is outside gamma, and of course, there are some points on the curve gamma itself that I have to take care, and this is union is disjoint union. So, in the area included by that gamma, we do not consider the points on the curve. This looks like very simple, but it needs a proof. And it says also something more, that is interior of gamma is a bounded region. Okay? All of us understand what is bounded. Exterior of gamma is unbounded, and third, both region interior gamma and exterior gamma are connected. Okay. So, this is the famous Jordan curve theorem, and we use it in every part of mathematics kind of, and unfortunately nowhere it is proved, but it has a proof, and you can find a proof in some standard book, or but its proof needs some more terminology, some more tools of mathematics. Well, we will use this as usual, and with that theorem we define what is area of interior gamma. This is notation is A gamma. Well, as you know, if I have a curve like this, closed curve, A gamma should be, by simple calculus, interior gamma dx dy. Now, how do I express it in terms of the curve? Okay. Take gamma positively oriented. What do I mean by that? That is eta s points towards interior gamma at all s. So, if I have unit normal here, that should be pointing towards the interior gamma. If you see that this is the direction, if I take this is the, then this will be a tangent vector. So, eta s will be pointing towards interior gamma. Similarly, here is the tangent vector. So, eta s will be pointing towards interior gamma. So, positively oriented simply means if you take anti-clockwise direction. So, you are moving anti-clockwise direction. If you move the other direction, you will see eta s will go outside. I mean, it will point to exterior gamma. Now, there is this theorem in calculus which says that if I have such a region and I have two functions, smooth function, this is a statement of so m x y n x y, these are smooth functions on interior of gamma. Then Green's theorem states you that this relation hold. The integral, this integral, area integral is the line integral over gamma. Now, look back here. I have interior gamma dx dy, right. So, I need to find two function n and m here such that which is equal to 1, because this is just 1 here. Any two function n and m will do such that del n del x minus del m del y is 1. Then I can express it as line integral over gamma m dx and n dy. So, choose n of x y equal to half of x, m of x y equal to minus half of y for all x y in interior gamma. Then you see del n del x minus del m del y is just 1. So, hence A gamma will be given by gamma half of minus y dx plus x dy, and if you put it in the parametric form, this will be 0 to a x y dot minus x dot y dt, where gamma t I take x t y t. Okay. So, this is the area. Now, the famous isoperimetric inequality states that area of gamma, so gamma is a simple closed curve, is less than 1 by 4 pi L gamma square, where L gamma, recall, this is the length. With equality, if and only if gamma is a circle. See, for a circle, what is A gamma? This is pi r square, right, and what is L gamma? This is 2 pi r. So, then A gamma equal to 1 by 4 L gamma square. This is isoperimetric inequality. It is read in some layman's way that given all simple closed curve with a fixed perimeter. So, among the all simple closed curve with fixed perimeter, circle has the largest area, because then it will be equality, otherwise all the curves will have less than equal to. Okay. So, for the rest of the lecture I will prove this isoperimetric inequality. So, without loss of generality, let gamma be unit speed, that is arc length parameterized, unit speed parameterization, which have been referred to, with period pi. How can I do that? I have to change, just put t equal to pi s by L gamma, that will give you arc length parameterization with period pi. Whatever the period is, you make that period pi by this translation. Assume gamma 0 is 0, which is also equal to gamma pi, because it has period pi. This I can achieve by translation by right. Whatever the curve is, at 0 I can bring it to the origin. Now, consider gamma t as two coordinates, there is two coordinate x t and y t, and I put x equal to r cos theta and y equal to r sin theta in polar coordinate. So, r and theta both functions of t. Here is the picture. So, this is my gamma, this is the angle theta it makes tangent, and this for particular point x t y t I put in the polar coordinate. And what I do here, this is at r, I draw a perpendicular, at this point it intersects the curve and I join these 2 points, and this angle I call theta, which is the angle between x axis and the tangent vector. So, this is the tangent vector at t 0. Okay. So, what do I get from these two? I get x dot is with respect to t, right, x dot square plus y dot square equal to r dot square. You must verify this part, theta dot square, verify, and you also get x y dot minus x dot y equal to r square theta dot. Now, what is t? T equal to pi s, this is a translation we have made, L gamma. So, that will give us this quantity r dot square plus r square theta dot square equal to dx ds square dy ds square ds dt square, which is equal to, you can easily calculate, L gamma square divided by pi square, correct. Why is this so? Because gamma is unit, we have taken unit speed, note This is the norm of gamma dot s, norm square. So, therefore, I get this is equal to L gamma square by pi square. Now, what is A gamma? A gamma is half x y dot, just now we proved x dot y dt. This was done in here. So, which is equal to, by this equation, half of r square theta dot dt. So, L gamma square divided by 4 pi minus A gamma. So, compare this to equation is equal to 1 by 4 0 to pi r square plus r square theta dot square dt minus half 0 to pi r square theta dot dt. Check. This follows from whatever I have written down from this follows. Let us call this is equal to 1 by 4 I, where I equal to 0 to pi r square r dot square plus r square theta dot square minus 2 r square theta dot square dt, which I write it as a 2 integral 0 to pi r square theta dot minus 1 square dt plus 0 to pi r dot square minus r square dt. Now, look at this integral. This is square of something integral. So, this is always greater than or equal to 0, because positive quantity. So, and what about this quantity? If I show this is greater than or equal to 0, so if this is greater than or equal to 0, I will get this fellow is greater than or equal to 0 and I will get my isoperimetric inequality, correct. If I show this is greater than or equal to 0, then I will get this is greater than or equal to this always. Now, this is a consequence of so called Reitinger's inequality, which says suppose I have a function f from 0 to 2 pi to r, which is smooth with f0 equal to f pi equal to 0, then 0 to pi df dt square dt is greater than or equal to 0 to pi f t square dt. So, take r equal to f, this will give you that 0 to pi r dot square minus r square dt is greater than or equal to 0. Reitinger's inequality, I put it as an assignment problem. This is just doing some manipulation. So, that and it has also the part of inequality, Reitinger's inequality, equality, that is equality here in star if and only if f t equal to a sin t. Now, go back here. Reitinger's equality will tell you this is now if I can move by Reitinger's inequality, this is greater than or equal to 0. This is greater than or equal to 0 because of the positive quantity. So, I get isoperimetric inequality that this fellow is always greater than or equal to this fellow. Then when is the equality? equality is both. So, I will have equality in isoperimetric inequality if this is 0 and this is 0. So, that means in isoperimetric inequality equality happens only if 0 to pi r square theta dot minus 1 square dt equal to 0, which implies theta dot equal to 1 for all t, which implies theta equal to some t plus alpha, some constant, and 0 to pi r dot square minus r square dt equal to 0. But now from this part this follows that we must have r equal to some a sin t, which is sin t, which is equal to a sin theta minus alpha. Now, what is this? R t equal to a sin theta t minus alpha. What is the equation of this? This is a circle with diameter a. So, that is the proof of isoperimetric inequality, which, as I said, in layman's terms says that among the all closed curve with a given length, given perimeter, circle has the maximum area. That ends this module for curves and surfaces. Next time we will start with surfaces.